how do you deal with these big, complicated resistor circuits? I'm going to try to talk you through a more complicated analysis. We're not quite going to do it out in full glorious detail, but it can feel like a little bit of a jump from combining one or two resistors with a battery to suddenly getting, say, 6 resistors and 2 batteries. So the first thing, as always, is your modeling and simplifications. We pretty much always get to talk about wires as ideal. If there are resistors in your circuit, you should be able to talk about your wires as ideal. The next thing is that ideally your batteries are also ideal. And remember that that just means internal resistance is equal to 0. If you have resistors in your circuit with more than a couple of ohms of resistance, that is a great simplification to make. So the other thing that you're going to want to do with the simplification is when you draw your circuit diagram, feel free to lay out wires that are straight, make your components placed a little bit better so that you can actually see what's going on in the circuit. Remember, it's okay to move the component from the left and switch that with the component to the right, as long as you're not changing how they're attached to one another. Right? Junctions are important. So again, the analogy I made before was imagining a bunch of beads on elastic string. You can stretch it out, you can move them around, but you don't want to actually cut the string or tie any new connections in it. Now, one thing that's important when you're starting to deal with these more complicated problems is to make sure that you're really labeling everything. That includes potential differences, resistances. Feel free to use variables. Now, right now, we're only dealing with resistors, but eventually you're going to have capacitors as well, and currents. And make sure you specify a direction with your current. So then, you look at that and you start mathing it. And the math is coming from Kirchhoff's laws. And remember that Kirchhoff's laws were basically the loop law telling you about potential difference and the junction law telling you about current, which I don't see here, but I promise it exists. Oh, I guess it's down here. So in general, the way you're going to do this is reduce the circuit to the smallest number of equivalent resistors. That's usually going to be 1. It might not be if you have more batteries than that, but that's what you're going to want to do. So make it as simple as possible, no matter how complicated it began. You're going to ideally get it to something that looks like this. And from this, obviously, when this is E and this is R equivalent, it's really easy to figure out what that current is, right? I, in that case, is just your EMF over your equivalent resistance. But then you go back to your crazy, hard, complicated thing, step by step, figuring out the current through each path, right? So this is the rebuild the circuit. And then looking at different potential differences. And I can't give you a detailed recipe since it really will depend on the circuit that you have in front of you. So I'm going to go through the example that the book does that will hopefully give you a little bit of a feeling for this. But at the end, this assess step that we frequently don't worry very much about, that's really important here. You should be able to look at your results and everything should make sense. That your potential differences should sum to 0. Anything in parallel should be the same. Your currents should actually work. So let's look at one more concrete example. In this circuit, I have 1 battery and 4 resistors. This is not the hardest circuit I could give you, but it's not one you can do in your head. And note that in this case, the question is asking you to find the current through and potential difference across each of the resistors. That's not something you can just look at and know the answer to. You really have to work this out. Keep in mind that a different question that could be asked about the same circuit is to find the power dissipated in each resistor. Now, if you are asked to find that, you would still need the potential and or the current through each of them. So that's really the same question. So in thinking about this, there's a couple of things. First, you want to think about your modeling and simplification. Is it reasonable to say that your wires are ideal? Yes, it is reasonable to say that your wires are ideal because whatever resistance your wires have is much, much smaller than the resistances in your circuit. Is it reasonable to say that your battery is ideal? Yes, again, whatever internal resistance that your battery has is only a few ohms, so it's very small compared to all of this. So the next step, right, the thing that you need to know is what is that current? What is the current out of the battery? Now we can call this I0, but now where it's going to get complicated is I0 is going to split into, say, I1 and I2. Oh dear. And then I1 gets up here and splits into I3 and I4. Okay, they come back together, so this here is I1, comes back, and so this last bit, we're back to I0. But you can see that we potentially have 4 different currents to worry about, and we have 4 different potential differences, maybe, since we have 4 different resistors. So we need to simplify, since we have to start by figuring out what I0 is. This is where you want to identify the way to combine this down to one equivalent resistor. So the first thing you want to combine together are these 2 resistors in parallel. You make that one resistor, and now you see, okay, I have 3 resistors, but they're not quite all in parallel or series. These 2 are in series, so you combine them together into one resistor, and now you see that you have 2 resistors in parallel. You combine it down together into one resistor at the end. So make sure that you understand this process, and be careful. You can't just write down one simple equation for all 4 of these. You really want to think about going step by step. So now that I have one battery and one resistor, I can figure out what current is flowing, and then I work backwards to think about my potential differences and my currents. Typically that's going to involve a lot of calculations, not just labeling pictures, but here we're just looking at the picture. Keep in mind that having really good pictures are important, that if I only drew this, it's hard to keep in mind what all of these different equivalent resistors actually are. So please draw pictures when you're calculating this out. Now, just to notice that we're actually starting over here and going backwards. So don't try to read this from left to right. So we had, from the previous slide, our single battery and a single equivalent resistor. Note that we know the potential difference across that resistor. We know its resistance, and so from that we find the current. Now we start moving backwards. Remember that the step before our single resistor, we had 2 800 ohm resistors. They were in parallel, which means that whatever potential difference you have here is the potential difference that you have on each of those 800 ohms. We then can figure out what the current through each of those resistors is. Note that it's half of the total here. That makes sense. Well, now, this one here, this 800 is actually one of your true resistors, but this one is still an equivalent. So we break that into its pieces, keeping in mind that the same current flows through each piece. So we're keeping this, and note that that is then the current flowing through this resistor and that resistor. Since we know what the resistance is and the current, we then figure out what the potential difference is across each of them. Note that it's 3.6 and 8.4. That adds to 12, which we do expect. Finally, we need to break this one down, which was an equivalent resistor, into its 2 pieces, which were 2 resistors in parallel. That means that you're going to keep your potential difference, but your current is going to split. So here we know it's 15 milliamps. By using the potential difference and the resistance, we get 6 and 9, which sum to 15. This is then our final circuit. So again, the way to get this is to really go through all of these steps. You can't just start the circuit and write down all of these things or do simple calculations. So the place where students mess up the most here is by trying to take shortcuts that don't exist. This is a fairly long process, and it's one you'll get to do a few practice problems on.